Okay, so I guess we're ready to start this afternoon session. We have Alessandro Torielli, who is going to tell us about massless form factors in ADS3.
Thank you very much. I'd like to start by thanking the organizer. It's a great pleasure to be here, to be back home in Berlin at this very nice conference. So I will try to present some work I've done mostly in this paper on form factors in massless relativistic ADS3. But this is somehow, I've used a lot of results we've worked out and also other people have worked out throughout the years, and a lot of these people are in the room. I'm lucky because this morning it was basically ADS3 morning, so a lot of the introduction has been done by beautiful talks of Sergey and Fiona, so I will not need to introduce much more, but there's also the talk by Alessandro Sfondrinis at IGST that highly recommended. So let me give a quick outline. I will focus out of the many S matrices that Sergey presented in his talk. I'll focus on the massless part, and let me just maybe put into focus what my aim is. I think it's now quite established in the community that these massless modes are particularly interesting and probably the most strikingly new feature of these ADS3 and also ADS2 models. So a lot of the interest now, at least for me personally, is to try to understand their role and how to study them, because they seem to be quite anomalous in some sense. They don't fit into the standard way we used to think of ADS-CFT integrability. So I'll focus on the massless S matrices, just massless part of what Sergey said. And my interest in this talk will be to try to probe them in some other way. And another way of the traditional ones that one can study them is to study form factors, which are then the gate to correlation functions. So I'll try to test these modes with some form factor study. This is, again, not a new thing. Alessandro, Burkhard, and the student, Denis Leplat, they have done very lovely study of form factors as well. So the more information we can get out of these massless modes, the better, hopefully, we will understand them. So I'll describe a bit the form factor program, and then I'll try to describe the solutions to the form factors relations, starting with 2-particle and then 3-particle form factor, and then try to generalize. But before doing that, let me take a moment to just summarize a bit of the standard lore about massless integrability. Since we have to deal with these massless modes, or as Sergey rightly pointed out, these are gapless for the moment, let's try and see whether in the literature of relativistic systems, relativistic field theory, anything was said, and in fact, a huge amount was said. So let me quickly point out a few milestones of what one can read in the literature about massless integrability. In a relativistic field theory now, so away from ADS, we have, if you have massless particles, they have this simple dispersion relation in 1 + 1 dimension, E equal plus minus P, and you have this classic splitting between right movers and left movers. You have this cusp at the origin, and if you read the paper starting with Zamolodchikov, they give you a hint of how to deal with integrable S matrices with massless particles, because as it was pointed out, I think in one of the questions, some of the axioms fail because they're based on the mass gap. So how should we think of massless S matrix, massless scattering? The idea, summarizing, is that you have to split. So if you have left movers scattering with left and right with right, then your standard perturbative intuition of wave packets colliding fails. This is now a purely non-perturbative sector, which still exists. So in your theory, there is a sector, just purely left, and right, still described by some S matrices, which at that point become just some formal solution, well, not formal, the still functional solution of the Yang-Baxter equation. In the left versus right scattering, then you do have a perturbative intuition. You could set up your usual perturbative S matrix. But again, because you don't have the mass gap, it's a bit unclear whether a lot of the theorems of standard integrability, Parquet arguments hold. So you have to do some work here. And I'll give you an example on the next slides where you can construct a left with right scattering. Again, this is just fishing in the literature of the old gods and see what they told us. But the point is that you can take your solution, your S matrix. If you do have a massive system, you could take a limit, a sort of boost, to boost your particle to plus infinity rapidity, minus infinity. You get all the possible combination, left, 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 right, and so forth. You still get 4 limiting S matrices, left with left, right, right, left, right, right, left. There's still solution of Yang-Baxter. Well, the left, right, and left, left will be mixed, but okay. They are solution of some algebraic equation, and you can still think of them as matching condition of some beta wave function, so you can construct the states. What the meaning is a bit unclear, but you have this mathematical structure. It seems that the best way to think of them is the following. If you focus on the left, left, and right, right, you can easily show that the S matrix in this sector with the dispersion relation E equal plus P or E equal minus P becomes a sort of scale invariant object. You can reabsorb in a shift of the rapidity any change in the mass. But since the S matrix is of difference form, you will not notice. So these left, left, and right, right S matrices belong more to a critical theory. So you basically describe a CFT in the left and right sector using tools that are more properly designed for integrable systems, for massive ones. But you still hold on to them and use them. In fact, a phrase which I've taken from Zamolodchikov, it is fruitful to use these S matrices to just compute observables in the CFT. And there's also this series of very beautiful papers where you can actually see the interplay between quantum groups, CFT, integrable structures very closely. So this was put to fruition very much. The other sector would be the left with right and right with left. There you can still construct them. There are, again, works that show what kind of axioms should be given or how the axioms of integrable models, the massive ones, need to be slightly adapted because the analyticity structure of the S matrix is a bit different. But these ones will sort of remember a scale still. While left, left, and right, right, you can easily show in one line that they're insensitive to a rescaling. These left and right, they still feel a scale. So the idea is that they can be used to describe massless flows, renormalization group flows between UV and IR points. And this was also done in a series of many papers. Again, people in the room, I'm sure, have constructed such things. One typical example, which was very pedagogical for me, was this paper by Zamolodchikov, the tricritical to critical Ising. And this is basically the S matrix that Zamolodchikov uses to describe this flow. You see, it's a very simple pole, and it satisfies, this is in the Mandelstam variable, we are relativistic, and it remembers the mass, just this single parameter, which you can use to basically dial yourself through the flow. It satisfies certain property, crossing, unitarity, which become very simple. Here you see the massless dispersion relation for right movers. You see E equal P equal e to the some rapidity plus, E equal minus P e to the minus rapidity minus. This would be the left movers. The Mandelstam variable will become very simple in the rapidity difference, and in the theta plane, this is just this very simple factor. So this S matrix can be constructed just from first principle of a slightly adapted set of axioms adapted to the massless case. You have in the Mandelstam plane some cuts that disappear or coalesce to become the entire real line. You have to adapt a bit. You don't have the usual mass gap in the Mandelstam plane, but in this paper, oops, wrong button. In this paper, it was indeed constructed. And what do you do with the S matrix? You put it in the TBA to compute the ground state energy. And in this case, it's still difficult, but you can do the analysis a bit like what Dan was showing. There are now very powerful methods to deal with simple TBA in one variable. But in this case, with the standard D-logarithm trick, Zamolodchikov found the UV and IR behavior of the ground state energy, and this has to be interpreted as a C function. According to this formula, when you're close to the endpoint of the flow, this ground state energy, purely based on dimensional analysis, will pick up the central charge of the CFT. So if you read off from the TBA what this number is, you can evince the UV and IR central charges. And in this particular case, it flows from this to the Ising, just a free fermion. Okay, so this might not be entirely relevant for ADS5, but in some sense there will be some realization of this, not exactly this, but I thought it was useful just to know what came before, just to set what typically the literature understands when one deals with massless particles in integrable systems. Okay, so now I'm going to switch to something that indeed Sergei and Alessandro, they explained in their talks, so I'll be very brief. In fact, they were much more detailed than me. They put all the U1s as well, but we deal with ADS3 cross S3 cross T4. There is also this other background, which was briefly mentioned, and many more in the talk of Fiona. You have some superconformal algebra. It's some D to 1 alphas in this case, and you can contract if you send alpha either to 0 or to 1 in this PSU1, 1/2, 2 copies of the T4 background. You can do the BMN analysis and find the BMN spectrum, 8 boson and 8 fermion, and you find these massless, gapless excitations. And they are actually more in the case of T4 because some have mass alpha 1 minus alpha. So again, I recommend you to go back to the talks of Alessandro and Sergei to do all the details. I will not be focused very much on this. This is just for me the starting point because I will want to focus on these gapless modes. Okay, so as it was mentioned, to build an actual S matrix, now let's assume that we are still, for the moment, in the massive case. Then you have to construct, you have to make a choice of the vacuum and see what the symmetry is that preserves the vacuum, and you get 4 SU1/1 centrally extended in various ways. And here, instead of giving either the U1s or the commutation relation, which would be the proper way, I just gave a mini representations. You have certain supersymmetries. These are fermionic generators, Q left and Q bar left, or S left, Q right, and S right. They commute like this. They generate the central element, and this is a sort of fundamental representation with 1 boson and 1 fermion. So ultimately, I'm going to strip down all the complication, which has, of course, to be dealt with, just to this mini problem, from which, combining various different representations, you can then build up the whole thing again. But for me, I have 1 boson, 1 fermion, some representation satisfying this, because now I'm still massive. So this basically is very similar to ADS5. You have to specify the coproduct, which is the way your symmetries act on 2 particle states, and it's again very reminiscent from ADS5. You have these braiding factors on the supersymmetries. There's various frames you can write it, the central charges. So this will generate for you some equations which you need to solve, and you need to find the S matrix from the coproduct. So that. Another thing that was mentioned, very important, is the type of representations. And there are indeed, well, two types of massive. Here I've only written one with the m squared, but you have the mass +1 and -1. And this is the massive one, this dispersion relation which appeared before. It's the usual radius 5, just the mass here. Well, it's also 1. And it has this interplay between, it looks a bit relativistic if you go to small momenta, but it looks lattice, very much, in fact, like Ising model in some magnetic field, if you stay away from BMN. X plus, X minus, and the various constraints that had already appeared. The massless case was also discussed, and you reduce this to this dispersion relation with the modulus, and that gives you the splitting in left movers and right movers, and you have to, you can use this x variable, x plus 1 over x minus, and you have to remember this sign according to this splitting. I will actually be focusing on even less than the whole story. I'll just be doing the right movers. That's enough for my purpose. Okay, so in this case, if you just focus on, so from now on, I only do massless right movers. So I can simplify my formulas. I have positive momenta, so I can tell Mathematica full simplify. And everything is positive, and I get this representation for the supersymmetries. And now I can see the matrices, how they are, and this form. And already a nice thing I noticed, which was picked up this morning, H becomes a sort of global term, a factor in the supersymmetries, and it will disappear from the S matrix. So it's nice to see it already here. And here I'm still writing in terms of momentum, so that it's still a natural thing to do if you're still thinking about ADS5. Also, the central charges simplify. And I write the S matrix. Now, this is the S matrix you get from the coproduct in terms of momenta. This will not turn out to be the most useful variable, as was mentioned and as we will discover. But for the moment, it's useful for me because I want to make an argument of limits. And I need, for the moment, just to see, and you see, it's not difference form, of course, but secretly it is. But it's nice in terms of momenta. This tells a lot to me. It's quite a nice matrix to work with. Okay, so we'll remember what this is, because now something very strange happens, which did not happen in ADS5. So if we look at this, this again, I've taken the same chirality, we would say, left. In fact, right turns out to be related. It's very, very similar. So what I do now, I do what I would do, a check in ADS5. I take the BMN limit, small momentum, and also scaling with H, which plays the role of basically the TOF coupling. This is the BMN momentum the BMN limit I would do to get a relativistic dispersion relation, because that's exactly what I would do here. I would send P as 1 over H. That gives me m squared plus p squared. So that I would do, but normally in ADS5, where all the excitations were massive, typically this trivializes the S matrix. So you do indeed get a relativistic theory with a relativistic dispersion relation, but the S matrix is trivial, so you get just free particles. For massive modes, this is again what happens, and you can understand it very easily because of this. The S matrix is written in terms of this variable, and as long as this is non-zero, something else will go to 0, but this will remain, and there'll be no possibility of 0 over 0. The mechanism is that as long as this thing is finite, it will destroy any 0 over 0, and so you will get a trivial S matrix. But if, so this happens certainly for the massive modes. So all the massive modes basically become non-interacting in the BMN limit. Let's look at the massless modes. Now, the massless left and right, as we said and as we had at the beginning, they do remember a scale. And as long as you do remember a scale, then this BMN limit will trivialize the S matrix. Because, again, you've left the denominator and numerator. You'll never get a 0 over 0. So, okay, the left and right scattering trivializes, and this indeed is found in perturbation theory. The incredibly interesting thing was to realize that left and right do not. And you can see this very easily, because if I take p to 0, I get some nice 0 over 0, which will give some finite result. In fact, I can even skip ahead, and this will be the final result, because I can say that p is epsilon q, h is speed of light over epsilon, and I get this result. Now, look at how nice it is. The supersymmetries, which used to have sine p over 2, will become square root of q. Q is my BMN momentum. So they become some n equal 2 supersymmetry, relativistic supersymmetry, which typically go as e to the theta over 2. The same with the energy. The energy, look, that becomes relativistic, of course. But the S matrix or the R matrix, you can permute and go from one to the other. Well, this will become something. The 0 over 0 survives. And in fact, from here, it's quite nice to observe that with a single move, which is the same move that makes this a relativistic superalgebra, makes this a beautiful relativistic S matrix. Now with this thing, you see this is scale invariant, because you see it's homogeneous polynomials. So the scale also has disappeared. Not only h, but any mass scale has disappeared. If you try to reinstate a scale in the dispersion relation, think of this as e to the theta. Well, you can reabsorb it by shifting theta, and the S matrix is of difference form. This theta is the difference. So the scale is washed out. Yes? Yeah. Here, indeed. Here I'm just doing the right mover, so momenta positive. Exactly. So I find a very nice relativistic S matrix, very simple, conformal. I am at the conformal point. Why? Well, because of the common law we said at the beginning. The left and right, so the massive have gone. They have disappeared from the spectrum. The left and right massless do not scatter, because BMN limit trivializes left and right. But left and right remain. That is a CFT. So immediately the question was, what kind of relativistic CFT is this, and whether we can study it. So here I've tried to summarize a bit some of the ideas which we came across. And again, let me stress that unfortunately in ADS3 there's already a scarcity of data to compare with. This is a case where basically it's impossible to construct data because it's a non-perturbative object. The perturbation theory is trivial by construction. So I'm probing something which I have no way of checking if I don't know the dual CFT. In fact, I would have to identify in the dual CFT some kind of subsector which captures this worldsheet CFT. This defines a worldsheet CFT inside the theory. So the best we thought we would do with Diego and Bogdan was we compute the TBA, which now becomes feasible exactly because you see once you have this nice dispersion relation, with e to the theta, then this becomes what it's called, I learned from Davide Fioravanti, the conformal TBA. You can rescale all the mass scales away, and you're left with just an integral, which you can do. And that integral, with some pain, actually can be done. The same type of pain well, less than what Dan was showing. We don't need to do the expansion. In fact, we could not do the expansion because there's no expansion parameter. This is a conformal TBA. It's all or nothing. You have to solve it exactly. But you can. Diego was really the magician there, and he found some result, C equals 6 for what it matters. There's nothing to compare with. So, but it was nice to see that it could be constructed. And it seems to realize exactly the Zamolodchikov idea that we're describing some kind of CFT2, but not the CFT2 of the boundary, some worldsheet CFT in terms of a TBA, and it captures some kind of small momentum excitations, which is non-trivial. It survived the BMN limit. There's some remnant. This is the exact BMN limit, so the strict limit, not near BMN. That's just what's left at the end of the limit. Observation, which will turn out to be interesting later, is that this S matrix, some of you pointed it out to me at the time, if you forget some signs, if you put I and minus I here, I think you get sine Gordon, soliton anti-soliton, at a very special point, which is the n equal 2 supersymmetric point of sine Gordon. There's a coupling. When the beta squared is this number, you get an enhancement, n equal to supersymmetry, and that seems to be related to the fact that the SUQ2 coproduct, you know, it's deformed by Q to the Cartan. At this particular point, it simulates a fermionic. So having Q to the something becomes sort of a -1 to the F. But I've never really managed also Suvajit and yeah.
You mentioned C equals 6. This has to do with 4 plus half 4.
That's a natural conjecture, yeah. In fact, for a while, we entertained the idea that this could be just a bit of a complicated way of writing the free theory on the torus. So it does happen in the literature that you find, but we never really managed to make it precise. So, okay, so this is the S matrix. And now the dressing phase. This is very important, in fact, because it was discussed by Sergey and Alessandro. And after their paper came out, it gave me personally a lot of thought. So let me show the cross. So I have to put in front of the S matrix a dressing phase. Here I call it phi, but I could call it S of theta now, because everything I assume, and again it's an assumption, that will depend on the difference. This is in fact, incidentally, not the assumption that is done in that work. The crossing equation which I write down is this one, and has this factor I, which for our situation comes from a particular choice of the Hopf algebra, and in particular from not identifying the Rho and Robard representation. So there's a certain subtlety in identifying representation. A certain choice was made in this paper, which is definitely more natural from the full string theory point of view, because it talks very well with the massive modes. But rederiving everything from scratch from this BMN limit, one can construct a mini Hopf algebra only based on this problem, and that consistently gives an I here, which fits with a certain literature, which I read a lot about when I was doing this. And these are the n equal 2 massless flows of Fenley interligator. They have a very similar S matrix. It's what they call the fundamental n equal 2 S matrix. That has a similar crossing, and it has a one factor of the Zamolodchikov sine Gordon factor at special coupling in front, which comes from this. This is exactly the equation that the sine Gordon factor satisfied, as Sergey showed. So we don't have the minus, which would require inserting the Ising factor, which in that Frolov-Sondrini need. So it's a different structure. This is less natural from the string theory point of view, more natural from this n equal 2 literature, whatever. It's difficult to, but certainly their structure is more natural when seen from above. And also another comment is the BES factor. You see, we not only not have the Ising factor A of theta, we don't have the BES that would break difference form. And indeed, from this perspective, there was no necessity, but we understand that from the string theory, it should be there. So from this point on, two structures depart. And I worked on this one, and I want to try and find some insight from this one, which is a bit simpler. I wouldn't know how to do BES at this point for what I'm going to say. But the hope is that the tools that I develop here for form factors will be useful either way, because then, because of factorization, we could just pile up some of these functions that I'm going to find, and hopefully they'll give whatever answer they need to give. But yes? I did some rough check. I need to double check. It seems to me that it's taking a shape again as some sine Gordon, but it seems a bit, I don't know. But I don't trust myself on that. It's quite a delicate limit. But interesting in the BMN limit, my belief is that if it is anything, it will be of difference form in BMN only. Simply because there's nothing, well, again, it's just speculation. But it would certainly change the central charge. All the TBA calculation we did will be modified. In fact, even just by the Ising factor. Another thing was this gamma variable. So this, you may say, indeed, is good for BMN, but can we do anything if we move away? And here we have the very strange situation from the point of view of standard integrability, that when you move to mass, when you move away, you break relativistic invariance in principle. But we found, indeed, with Fontanella, this variable, and this recasts this formula in difference form. So if you use that gamma variable, and again, this is written only for the right chirality, then you get that the massless S matrix in non-relativistic limit is again of the same form as this, but here you have gamma 1 minus gamma 2. That gave a very nice way to recover the BMN limit, because if you see what happens in BMN, again, I'm doing the right movers, I send P to positive 0 plus, this develops a very large part and a finite offset. That very large part works as a boost. It does what in the homological literature is sending theta to plus infinity to boost to the speed of light. So in a sense, this is a very nice relation which tells me now send P to 0 means boosting to relativistic, and theta is what remains once I take away the infinite boost. And that's going to be the theta 1 minus theta 2 of this variable here. That's going to be. But of course, the S matrix is of difference form. So whatever large offset I get to gamma, it cancels out. So the form will remain the same. It's a very simple way a posteriori to justify that the BMN limit in this left, left, right, right is exactly the same as non-BMN. The dressing factor also will inherit the structure, but of course with the difference that we said. The only trouble which sort of broke my dreams was that the dispersion relation in massless non-BMN is non-relativistic. So yeah, it's this interesting thing which will go to relativistic if you go to the infinite boost. But OK, one has to live with it. So it's very easy to get confused and excited and think that one has recovered relativistic invariance. But as we were then reminded, we need to be very careful because the theory is secretly non-relativistic. It's just of difference form. It looks exactly as relativistic apart from the dispersion relation, but it secretly knows the scale. You see here, now it remembers the scale h. And in fact, this bites you or bites me when you do the mirror. I thought naively, a mirror is just the same because we are pseudo-relativistic, so there's nothing I need to do. That was incorrect. You need to do mirror and you get mirror gamma variable. So the mirror direct invariance is only in BMN now. That's why I can safely say that this is a massless theory, because now I'm relativistic again, and this is a gapless theory. Okay, and then TBA, and then Alessandro and Sergei also found this very nice massive version, which we heard about. This was, okay, so let's take stock, and I've lost track of time, but okay. It's not, yeah, it's shifted. 20 to go? Perfect, thank you. Okay, so I've managed to convey the main message I wanted, that we have this nice CFT with the debate on the central charge, but and the factor which will change the physics, but still, it's the main principle remains. In fact, I should say that obviously the same structure in Frolov-Sfondrini will remain, that in BMN, the left-right will decouple, and the right-right, that's just a structural thing. But you can check in the S matrix. So what do we need to do? We seem to have found a theory at the critical point, some CFT sitting there, and we need to check, or in fact rederive what the number is. 6 is basically the first thing that came. We're quite confident, but again, it's based on the old dressing phase. The most important thing to me is that difference form gives a chance to test a lot of the proposals using a setting. It's a bit of a toy model for ADS5, where you go back to relativistic and play with very simple functions, and you could check some of the things that assumes very difficult form in the full theory. For instance, if you now remember that to solve the theory you need correlators and construct the Whiteman functions and the form factors, which you should do, then there is this very nice work by Burkhardt, Denis, and Alessandro, who applied the hexagon program to find a sort of hexagon form factors in ADS3. That has become, to my mind, a bit of the substitute of the form factor program, of the form factor axioms in ADS. It's tailored to the Joukowsky variables, the mirror theory. It works very well. But it still remains very difficult because typically when you do a massive calculation, I read the papers and it's very complicated. And in the end, the tests that are made are perhaps on some protected operators whenever one can have some handle. But this is now a testing ground, because is it possible to push the hexagon in this BMN limit where it needs to return to its origin somehow? It needs to return relativistic. And it also, you'll decouple the massive modes, and you'll be left with some objects which I assume will be non-trivial. So the same way as the S matrix, there should be some simple hexagon form factors in this BMN limit. So I'm proposing to the hexagon community some sort of conformal hexagon program or relativistic BMN hexagon program. Hopefully this will become an industry. It will not, but okay. So this would be a nice testing ground. But of course, at this point, the temptation to use the old form factor approach was too strong, so because we are in a relativistic theory, so that's what I did. I took this theory and subjected it to the Smirnov axioms and see what happened. The two things should talk somehow in some way. That's very interesting to me. Yeah, the same. A lot of what I will say is confined, completely confined to the BMN limit. So I'm expecting somehow to find the form factors for a conformal field theory, which, if I compute correlators, would give me the correlators of a conformal field theory with some typical behavior. But I'll never be able to reach the end. In fact, it's still so complicated that I cannot compute, not even any point form factors, but at least there's some machinery. And using the gamma variable, a lot of what I will say straightforwardly applies, except the fact that the moment you go away from BMN, left and right start interacting, and so you cannot factorize anymore left with right. So it's actually more complicated than it superficially seems. So let me quickly then review in the very last few minutes these form factor axioms as they were for relativistic models. And I refer to these very nice papers where you can find also a lot of the original literature. So the interest is to compute some expectation value of some local operators taken at the origin with the vacuum and some in-state of n magnon. And these magnons can have various polarizations. In this particular model, which I specify myself to, thetas are the rapidities, and now thetas are minus infinity plus infinity, because I'm already in the right moving sector. So P equal E to the theta, theta real. Alpha is either boson or fermion. So I'm doing a mini form factor for a two-dimensional space. Of course, I will need to combine them to actually do the full spectrum of 8 boson and 8 fermion. But for the moment, I'm doing the closest to sine-Gordon. This is going to be very similar to sine-Gordon form factors. And of course, the form factor, why are they useful? Because you can then, by inserting a full resolution of the identity and summing over, you can build correlation functions out of these form factors. So if you have them, and they you find them axiomatically from some properties, they're just some analytic functions, meromorphic, you then plug them into some sum, and you find your correlator. And again, we should not forget that we are dealing with a relativistic conformal theory, so there will be some conformal form factors. What are the axioms? The axioms are, as always, a generalization of the observation one sees in Feynman graphs, and then one axiomatizes this in properties of the actual analytic functions. So if you have a form factors of a certain polarization with a certain operator, and you swap two of the rapidities, the j and j plus 1, then it's the same as not doing it up to an S matrix factor. Every time you swap two legs, you pick up an S matrix factor. And here I spare you all the indices. There's some relation between the S matrix. We will be in the graded setting, so there'll be bosons and fermions. The swapping has to have a sign, of course. Then there will be the periodicity axiom. If I take the first of the in-states and shift by 2I pi, it's the same, modulo again a sign which I pick up by swapping with the operators as putting it to the very end. The operator is always sitting there, so we should not forget that it has some grading. Fermion could be fermionic operator. The form factor, of course, is an even function. It will respect the total fermion number. The super selection rule. It will have some Lorentz boost property. So if the operator carries a spin again in the two-dimensional sense, then if I do a boost of the rapidities, I will pick up the spin as a global factor. Typically, you continue the axioms. This is only some of the axioms, but there is also axioms about singularities. So the form factors have poles, and also, so the poles could be kinematical poles and bound state poles, but as it was mentioned in Alessandro's talk last week, you cannot have bound states of two massless particles, so here we don't need to worry about the bound state poles. the same way as the S matrix doesn't have bound state poles. There is a debate in the literature, which experts can correct me on, whether a conformal form factor needs to have kinematical singularities. And the arguments in favor, which I found in the paper by Musardo, is that the S matrix has the same form as the massive one, because you can take it by infinite boost, and left and right will not matter. So if the massive form factors have kinematical singularities, then the conformal ones might as well have them, because the S matrix has the same form. But I have a counter argument. Here, if I go massive, I break relativistic invariance, because in ADS, massive means having returned to ADS, non-relativistic. So I'm not quite sure. And just to ignore everything, I thought, let me put them in. So I've imposed, just out of generosity, that there are kinematical singularities. And they normally do like this. If theta 1 and theta 2 are in this configuration, particle, antiparticle, head-on, and alpha 1 is antiparticle of alpha 2, then you have a singularity and the residue, a simple pole, and the residue should have this complicated form with the charge conjugation matrix, identity, meaning all Kronecker deltas, minus all S matrices you pick up going around the remaining particles, times a form factor of 2 particle less. You see, 1 and 2 have died out, and I'm left with the 3 and n. It's a sort of recursion relation. Typically, it's used. Thank you. It's used exactly like this. In simple models, you find the first form factor, and then with some work, you just generate all the other ones by recursion. And again, you have statistical factors all over because you're permuting fermionic particles bosonic. So this is all the axioms that I will keep. And now I will not have time to show you the actual calculation. Maybe I'll just flash you the integrals. But let me tell you the problems that, at least to my mind, are a bit challenging in this setting. So the main power, but it could also be a drawback of this form factor program, to my mind, is that you find the solution first to the axioms, and then you worry later what the operator might be. So at this point, you see, I've never really told you what the operator is, except that these fermionic signs remember if you swap a fermion and if the operator is fermionic. But that's it. And of course, they know the spin. So I told you something about the operator, but not too much. The point is that this should be enough to find the solution and then go and scour the theory for a particular operator which fits very well with your solution. And typically, if you look at how it's done in the literature, they know so much about the theory that they nail it down in one way or another. It's either this momentum tensor, so there's not much of a choice, or if there is, very clever people find the right operator and then can check. But of course, the important thing is you need to have data point at the end. So if you say that, all right, you found a solution to the axioms, and this you claim it describes the energy momentum tensor, you better then go and check whether your formula reproduces the right correlator. And if you, for instance, if you have a Lagrangian, you could actually do perturbation theory and check. But we are again in that unfortunate case where we've made a limit at the level of the S matrix, and there is no way to take the sigma model Lagrangian and figure out which part of the fields this is. It's just a completely quantum procedure. So I don't know data points to check my operator, so I can just claim that based on just consistency, I found something that looks like a fermionic operator of spin 1/2. Hopefully, the more we accumulate evidence, the better it will be at checking these operators. Yeah, so we are exactly in the opposite situation. We're actually looking for the theory. We don't have the theory and looking for the form factors. We derive the form factors and then check, wonder what the theory will be. But certainly it is true that the solution to the form factor axioms are very constrained, and also because I haven't given one of the sort of axiom of relativistic S matrix, which is meromorphicity. Everything has to be analytic except poles in the theta plane. That, again, sets you into the right framework. And also, let me say a few more technical things about the fact you could say, well, but couldn't you just look at the literature and in Sine-Gordon you have a very similar S matrix? Basically, that's what I've done. I've taken these papers. They do form factor for Sine-Gordon in very much detail, and I've changed here and there the factors of I and minus to make it the S matrix that we have. And I thought that that would be a free ride, that I could just take the formulas and go with them. But the theory is actually very different from Sine-Gordon. In various aspects, Sine-Gordon is such that if you take the soliton-antisoliton S matrix, they are two fermions. That's why they're dual to the Turing model. So there's always a minus sign no matter whether you scatter. In some sense, my B and F are two F1 and F2 in Sine-Gordon. So that's already annoying. But also, they have a different symmetry. You can find in papers by Fendley, Interligator, and Saleur that the right setting for these models, for the ordinary models, is fractional statistics. You have some fractional fermionic number, while we don't have that. I haven't said that the coproduct in BMN limit completely trivializes, because e to the IP goes to the quarter goes to 1. So ours are bosons and fermions with ordinary statistics. Also, and this was the killer of the program to just borrow Sine-Gordon, the soliton is the antiparticle of the antisoliton. So F1 and F2, the kink and anti-kink, are each antiparticle of one another. So you can restrict the model, the problem, to a 4x4 matrix. We have boson anti-boson, fermion anti-fermion. So it's already a 16 by 16 problem. And in fact, that's the real complication, because you have a proliferation of form factors where you can put B or B bar, F or F bar in all possible combinations, and you have to solve for all of them. But I've tried, and somehow let me show you, well, you can find very quickly the minimal two-particle form factor. That's for free from this paper. If you can write your dressing phase like this, which we can, then the minimal form factor satisfying this with the right number of poles and analyticity on the real axis, well, analyticity in a strip containing the real axis, is this. That's a theorem. So you could do that. But this is just one of the building blocks. Let me just show you quickly the three particles. That's this nice story. Ask me later about this off-shell beta ansatz, which is beautiful. How you find, yeah. So this is the last technical slide. These are the three form factors for, you see, boson, boson, fermion, boson, fermion, boson, fermion, boson, boson, satisfying all the axioms, painstakingly checking that they do. And they have an integral over the auxiliary parameter of the off-shell beta ansatz, which is a very nice story. Functions, 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 exponential, exponentials, more functions, combined in such a way that they work, and with some contours which I spare. Okay, let me jump quickly then. Yeah, contour. Yeah. Okay, story. Okay, so you go through that machinery, you find some solution, and then, again, we're back at the beginning. We need to conjecture. So I found all those solutions, and as you can see, if you have boson, boson, fermion, the operator must be fermion. So at least I know some properties. I know the spin. But again, there's just three functions, and then I have some conjecture for the endpoint functions. But again, they're just there. They're in waiting for an operator to show up and claim them. And not only that, but even supposing you do find all the form factors, typically what you have to do is to construct the actual two-point function, for instance. That's the resolution of the identity you insert, and you have to compute this sum. This is again another difference from massive. Typically, if here you could have m cos theta I, that would be suppressed in R, and you could truncate your sum over form factors, and typically the papers then they plot them and they stop at the first few and they get nice agreement. This is not suppressed. In fact, this is divergent because I can rescale R away in a shift of theta, and I get an integral which is just infinity, so I need to IR regulate this integral. So there are some papers that show that surprisingly you could truncate even a massless form factor series and get surprisingly good agreement when there would be no reason for, because there's no suppression, but somehow the numerics. But again, I haven't done this calculation, and maybe let me put just a finite slide. I will not go through it, but there's so many things that one could do. F, yeah, this would be constructed via this. So F is this G where I fix the end. It's basically this, the triparticle. Ah, no, then I need some conjecture. And I have, in the paper I did, based again on the Sine-Gordon analogy. These are actually very similar to Sine-Gordon, nevertheless. Based on that, I conjecture what it could be at n, but I have no power to check all the axioms. It's too complicated. So the one is just a number. That's the starting point of the odd recursion. The two-point function, again, it's not just this, but it's some dressed version of this, so that's a bit more manageable. So if I were sure about the singularity, I could generate the recursion that then takes me to 4, 6. That could be done. Yeah, so a lot of things could be done, again, just to check not only these form factors, but all the properties of this point. But again, as it always happens, the complication of the calculation then obscures the starting point, which was how simple it was supposed to be, this theory, this conformal theory, but still it's capable of generating a very big mess. Okay, maybe I'll stop. Thank you.
Questions for Alessandro?
How does it connect with the quantum spectral curve? Means if one were to...
That I'm not sure. That I'm really not sure. In fact, not only because, but primarily because the quantum spectral curve does not incorporate massless modes yet. But even then, I'm not an expert, so I don't really know how from even the massive QSC one goes to the massive hexagon, for instance, or the massive form factor. That might be answerable in the literature. So somebody must have known that.
Any further questions? Then maybe I can ask a question. So it seems that in the end, I mean, you started talking about the ADS3 string, but in the end, the connection was sort of somewhat remote. How should I think about this? Should I think about it as some toy model for understanding a case, or can you relate this more precisely to?
I think that there will be a part of the string spectrum captured by this. Whether this will be too much of a simplified dressing phase, but the mechanism to go to BMN, left, left, right, right, that will remain in any theory with massless modes.
So this is some closed subsector or something that you can analyze on its own?
Yeah.
Any other questions? Okay, since we already had some questions, let's thank Alessandro again. And now we have a coffee. Okay, I guess we're ready to start the last talk for the day. So we have Saskia, who's going to tell us about topological defects and generalized T-duality.
Thank you, Linus. First, I would like to thank the organizers for this invitation to speak, but also for organizing this very nice conference. So today I want to present some work that we hope is nearly finished about topological defect and generalized T-duality. And this work in collaboration, with Thomas Remmel, that should be sitting somewhere here. Okay. So first, let me give some motivation, and I am lucky that I am on the third day of this conference, so you all have actually had pieces and bits of all these connected concepts that we have at this conference, so that we try to find integrable models that are deformed, have less symmetry, but are still integrable, and that is somehow related to this generalized notion of T-duality, which is known as Poissonian T-duality, and that we can formulate that into a double field theory and generalized geometry, and that maybe for some of us, the ultimate goal is to find some deformed version of ADS CFT where we have less symmetry, but we still have integrability. And the question I want to ask is, what happens to all these relations and all these bubbles when you add defects into the picture? And defects are very rich objects. They have different appearance, they have different definitions. So actually, you will also use different defects in different of these sides. So for example, for integrable deformations, you might wonder, well, we already have deformations inside the system. Can we add on top of that defects and still remain integrable? And actually, I answered this question already with Thomas, at least partially by constructing explicit example of defects that indeed deform these Yang-Baxter deformations. But today, I would like to focus on the other side of this slide and try to see whether we can find a certain type of defects, which are called topological defect, that encodes this generalized notion of T-duality and what its consequences are. Okay. So just give you to brief you a brief outline of what's going to come. So first, I need to introduce what the defects are and what topological defects are in particular. And then once I've done that, I can explain how I can realize Poissonian T-duality in terms of a topological defect. And the rest of the talk essentially will be about application and consequences of having these objects. But at the end of the talk, actually, I want to make a more general statement and walk away from a Poissonian T-duality and study something that's known as the notion of fusion on a more general level. Good. So, well, I think that you all have a rough idea of what a defect is, but let me be a bit more precise. So, I mean, simply when you have a slab of material, that material might have different phases on which it is. And these different phases then are separated by some boundary. And so that is our defect. So it's a kind of internal boundary for which the fields inside your system might change discontinuously, but it's still the same slab of material, so it should preserve certain properties. So in our case that we will look at, we will actually have two worldsheets, and they both describe a different model, and they will be separated by a line defect. And depending on what kind of properties they will preserve, they will have a different name. So you have conformal defect, you have topological defect, and you have integrable defect. And I would like to focus on topological defect. So maybe before I get questions about this, let me be clear that, so for example, integrable defects, they do what you think they do. That is that when you put them there, integrable defect will preserve the integrability of the whole system, so the two models plus the defect. On the other hand, conformal and topological defect do not, I mean, these adjectives do not refer to the whole system as a whole, but actually about special properties of the defect itself. So speaking about topological defect, I'm not speaking about topological systems. Good. But I actually want to restrict what kind of model we are looking at. So I will be looking at sigma models, like we had quite a few times already in the talk. And so that means that I will have a total system with, well, on the left, say, a model which is defined by a target space X to, from sigma to a target space M. Then another model that goes from sigma tilde to M tilde. And then I can see this thing as living in this product space. The product space is a product of the two target space. And then I need to take into account that the bulk fields on the two sides have to couple to this defect via a line bundle that has a connection A. And here it comes with the pullback. Perfect. So that's the setting. But actually, I do not want to work on a worldsheet. I want to work at the level of the target space, because there, at least for Poisson-Lee duality, I understand things better. And so what is then the topological defect in a target space? Well, then you just take this line, you map it to the target space map, so the product that you have now. And so it's going to span a submanifold in your product space, which are called Y, together with the induced line bundle that comes from the one on the worldsheet, which I will denote by the same letters. But okay, so still I want to preserve my certain properties, which are for us calculability. So the fact that it will be topological in particular will impose strong constraint on this pair that will determine the topological defect in the target space. So, and these I will explain a bit later in the talk. But first, let me say what topological defects are for the worldsheet. So there, a topological defect means that the holomorphic and anti-holomorphic components of the energy momentum tensor are going to glue nicely on the location of the defects. And okay, so what does that have an implication? Because that makes the topological defect interesting. Well, the name topological comes actually from one of these properties, because one of these properties implies that you can actually deform and move the defect at no cost. So it's a line, and you can do whatever you want. You can deform it. And one of the things we will be able to do is a concept of fusion, where we're going to joint defects together or joint with boundary conditions in one of the models. But that will be for the second half of this talk. What the other nice properties that is generally expected from these topological defects is that they encode symmetries or dualities between systems. And at the level of the worldsheet, this has been studied a lot by a lot of people, and it has been shown to realize abelian T-duality, Kramers-Wanier duality in more condensed matter settings, or theories that are orbifolds on each other. And these are just a couple of examples. On the level of the target space, when you don't have that much control on the worldsheet, it was shown that you can actually realize non-abelian T-duality and fermionic T-duality using a topological defect. Good. So that's all I need about topological defects. So now let me show you, well, not quite, because I still need to, yeah?
Sorry, question. You're saying you're going to look at topological defects from the target, but the definition of topological was about the worldsheet, so...
I will come to that. It's the second half of the talk. Yes, that's a good point. Well, I mean, this will be fine as long as we are at the level of the Lagrangian, what will be in the next slides. But when we will speak about fusion, it will be handier to actually indeed characterize them at the level of the target space, but I will explain that. Okay, so, oops. We need a few details about Poisson-Lee sigma models. So Chris already nicely introduced them, but let me go over it once again. So now we'll restrict even more the class of non-linear sigma model I want to consider, and I want to consider so-called Poisson-Lee symmetric sigma models. That means that I can apply a Poisson-Lee T-duality. And so I start with a target space, which would be a Lie group, and by solving some kind of equations, you can associate it to that a very special Poisson structure. And with this Poisson structure, I can construct this background with a bunch of constant E naught. And the very special things about this Lie group together with this special structure constant is actually that they come automatically with a dual group, which is denoted with G tilde, which again comes with its own Poisson structure P tilde. And it was shown by Klimczyk and Shevera that you can then write down an action that looks very much like the previous one, and these two actions then generalize abelian and non-abelian T-duals. Good. So here you might be a bit skeptical, or at least like, how do I see that it generalizes abelian and non-abelian T-duality? So the quickest way to go there is actually to invoke a larger object, which is the Drinfeld double. And the Drinfeld double is, in its easier form, just the product of G and G tilde. And by specializing this choice of a Drinfeld double, you can then see how abelian and non-abelian come up. So for abelian T-duality, you do the thing you expect, right? You want your background to be tori, so you just take 2 times n tori. And in that case, as Chris actually mentioned, the 2 Poisson structure or vanish or 0, and then you get indeed the relation you expect from an abelian T-duality. And for non-abelian T-duality, you will start with a non-abelian isometry, G, and then the second one will just be a U1. And then you can work out what that means with the Poisson structure, and you get the non-abelian T-duality you expect. So this generalizes these 2 cases. Good. So that's all I need with Poisson-Lie T-duality. Well, not quite. well, it's a canonical transformation, which is important as well, which I forgot, but that makes it even well, more like the abelian non-abelian case, which are also canonical transformation. But the thing that I really want you to remember from this bit is that this Drinfeld double is not only a nice Lie group, it's also automatically equipped with a symplectic structure. And that symplectic structure is, well, you can construct it using, in terms of right and left Maurer-Cartan form. The details are not that important. And it's called often the Semyonov-Tchernshansky symplectic structure. So the Drinfeld double is automatically a symplectic manifold. And since that name is too many syllables for me, it will be the STS for the rest of the talk. Good. Now, if you have questions, you have 5 seconds because I need to drink. Good. So now we have all the ingredients you need. So the questions that I raised already earlier, does there exist some kind of defect? Can we construct the defect that encodes Poisson-Lie T-duality? Then is the defect also topological? Because it is not automatic. It might also be conformal, it might be something else. And then if it's topological, then it has this nice feature of being able to deform it at no cost. Can we then say something about its fusion and what can we learn from that? And that will be the second half of the talk. So we showed that the pair that corresponds to the target space picture of a topological defect for Poisson-Lie T-duality is actually a space-filling defect. So it's a whole Drinfeld double with as two form that characterize the defect is this STS symplectic structure. And so that means that you have this action, and then you have to compute the equations of motions. And when you do that, you see actually that on shell, the conditions boil down to, you have to choose a particular solution. After doing that, the dust has settled, you can actually identify all these relations as a canonical transformation of Poisson-Lie T-duality. So it really encodes Poisson-Lie T-duality between this model and this model. And in addition, you can then, well, it's a straightforward computation that it's also topological. So we have a topological defect that encodes Poisson-Lie T-duality, and that then also has a feature of being, yes, Alex? Who has a mic? With encode, I just mean that so topological defects can separate systems that are related by T-duality. But you need still to be able to characterize that. And so this is the one that characterizes Poisson-Lie T-duality. That's the only thing I mean with encode. Maybe I should change that verb if it isn't clear then. Is good? Okay. Good. So, and actually, just by constructing this, we'll have automatically an identification of what the so-called Fourier-Mukai transformation is that's associated to generalized T-duality. So what is this Fourier-Mukai transformation? So for that, I need two facts. So the first fact is that, well, since T-duality and its generalization is a canonical transformation at the level of the NS sector, you kind of know what you need to do there. On the Ramon-Ramon field, Ramon-Ramon sector, it's a bit more complicated. And one of the ways to know how it transforms under T-duality, at least in the abelian case, it was shown some time ago by Hori that it's actually implemented by this so-called Fourier-Mukai transformation. So this Fourier-Mukai transformation is just actually an isomorphism between the cohomologies of two manifolds. And it takes this form. So let me just break it down. So it takes a polyform or a one form, whatever. So a polyform for a Ramon-Ramon field. It's with some map P1, it pulls it back to some product space of these two manifolds, where there it convolutes it with the kernel, and that kernel is actually what encodes the data of the isomorphism of the T-duality, and then it pushes it back to the other manifold, and you obtain the T-dual object or the isomorphic object. So that's what this term means, roughly. And the second fact we need, and you know, is that Ramon-Ramon fields couple to D brane charges. Okay, so that's the fact I need. And now we need to remember that this topological defect, well, I was able to move it around and fuse it. And one of the fusion things I can do is that I can place a boundary condition on one of the sides, and I can fuse it with the boundary condition. And so actually people in this defect community then thinking about this, like had the expectation and intuition that somehow the Fourier-Mukai transformation should be related to this fusion process. Because, well, this boundary condition is a D brane, fusing is doing T-duality, and somehow the Ramon-Ramon fields know something or feel the D brane, so it should somehow be related. And this intuition turned out to be true. And they could show that quite formally at the level of the worldsheets, that fusion was a kind of Fourier-Mukai-like transformation, so doing this kind of triangle. And then it was also argued at the level of the worldsheet that you also had a relation with Fourier-Mukai transformation, and a very tangible one at that. That in fact the kernel we have here that encodes the T-duality takes on roughly this form, which, okay, it has the B fields on both sides of your solution, supergravity solutions, for example. And the thing you need to add to have the kernel is the two-form field that characterize the curvature that characterize the defect. So the defect tells you directly somehow what the Fourier-Mukai transformation is. They did that for abelian T-duality, and later they also argued that for non-abelian T-duality. And so that means that since now we have the topological defect that encodes Poisson-Lie T-duality, we can directly make an ansatz for what the Fourier-Mukai transformation is for Poisson-Lie T-duality. Namely, that it is characterized here with F being this omega STS. And this ansatz actually agrees completely with the one of Alex, Chris, and Dan that they made from a completely different perspective, where they also said, okay, the kernel is the STS. Okay, it disagrees with another one, but I think this one is a bit more well motivated. Good. So, well, I just said that you can fuse this defect we have, the Poisson-Lie T-duality defect, any defect with boundary condition. That means in particular that we should be able to understand the Poisson-Lie T-duality transformation of D branes using this defect. And this you can indeed do, and let me show you how you do that at the level of the Lagrangian. So the way how to do that is to use a well-known method to encode boundary condition using a gluing matrix. So that means that you glue at the boundary the left and the right moving sectors by some R matrix. Okay, this R matrix is not anything. It needs to satisfy certain conditions that I know won't be important here, but it's not anything. And quite some time ago, actually, the Poisson-Lie T-duality transformation rule of this R matrix were already worked out, so these were known. And then we showed how you can realize that using fusion. So what you do is that you take this action, you perform a formal move toward the boundary, where then you get the equations of motion, and you encode the boundary condition in this way, and we get exactly the Poisson-Lie T-duality transformation rule that were derived before, but in this picture of fusion. Good. Okay. So, so this whole bit was more about Poisson-Lie T-duality. Now I want to spend some time about just speaking about fusion and how fusion happens at the level of the target space. Good. So this fusion thing has kept a lot of people working for many years, and it's quite well understood in terms of category theory and module theory. I don't need the details, actually. The only thing I want to say is that this thing is very well understood. But at the level of target space, I think it's fair to say that it's not understood at all, or it's very ill understood. And so our goal was to try a way to have a better definition, a better understanding of what fusion means, what it induces at the level of the target space. Since it should, anything that happens on the worldsheet when you have a sigma model should translate something into the target space. And the nice thing you might you expect is that if I denote the fusion process with a star, and so I'm fusing this defect 1 and with this defect 2 at the level of target space, is that when you fuse them together, you get a new defect or a superposition of them. And okay, so that's a picture because the other one was for 2 fusions. So now I want to just look at this, well, a particular case where I'm going to fuse the defect with some boundary condition. So, and this case was already studied in the context of Resomino-Witten models by Fuchs, Schweiger, and Waldorf. And there they thought, oh, okay, we have like a Fourier-Mukai transformation here. Well, the same should be true here. So what they wanted to do is actually just have an idea what this submanifold is you get after fusing 2 defects. And they said, okay, let's just make the simplest ansatz we can have. So we're going to use the projector as map to go up. Then we are going to take the intersection of the 2 manifolds, and then we're going to take the projection back. And that's what their ansatz, and they worked it out in certain examples, and it seemed to work. But I mean, this equation has actually problems. The first one is that nothing guarantees that the result of doing this thing is going to give you a submanifold. The other problem is that it comes really a little bit out of nowhere. Like, it has no foundation why you should write this and not something else or something more complicated. And the last thing is that you have no expression for the curvature that should be there. And so what I would like to claim here is that you can actually resolve this question by embedding this problem in generalized geometry, or more precisely into Dirac geometry. Okay, but to do that, I'll answer Dan's question. And I need actually two additional ways to have a way to characterize a topological defect. So we had already the one in terms of the energy momentum tensor, but I will explain in the next slide two other ways to do that were worked out by Kapustin and Setter, where first it's something in the product space where it boils down to a matrix multiplication, and then another one it's in generalized geometry that we will reinterpret in terms of Dirac geometry. And the reason why I want to do that is that while these two first ones are just useful to show the existence of the defect and that's its personality and topological, the last one will be the one that's useful for us to characterize fusion. Okay, so the first one, I will be rather short because it's quite, it's not super long to prove, but you need to crack the handle a little bit. So what you're going to do is that you're going to want to have a condition which is just in terms of this product space data. So you have the background fields, so the G and the G tilde of the two manifolds, and the B fields, and then you have the curvature of that's associated to the defect that you know. And then they showed that this condition boils down to doing a matrix multiplication of this kind of doubled metric and these two form fields, which is corrected by the B term. Okay, there is something that I don't want to discuss, is that you have a technicality that you need to do that on the screen distribution. It's not important, it's technical. If you're interested, you can ask after the talk. But the point that I want to make is that this is another way to characterize. It's somehow completely in terms of targets, the product space, target space quantities. And indeed, you can also, using this matrix multiplication, show that it's a personality defect and it's topological, the one we claimed. Okay, but what we really need is something that is a consequence of that, and that will offer actually a way to to have like a kind of universal description of boundary condition defects. And why do we want that? Is because if we want to have an operation between the two objects we fuse, which are these defects and these D-branes, they should at least be like the same object, because you can't have otherwise a well-defined product between them. And the claim will be that they will both be Dirac structure, as some of you actually might know for D-brane, and that's the correct way to look at it. Fine. So let me explain what that is. So the word volumes of D-branes, as you know, is characterized by some manifold in the target space and a curvature. Okay, it has many other properties, but for this talk, this is the only two data I want to capture. But defects, as I just explained, is exactly the same. It's just a submanifold, not on the target space, but on the product of the two target space with some curvature on it that capture the line bundle. Fine. Well, some people that know generalized geometry see me coming. You want, in some sense, to have that the vectors that are on the tangent space of this submanifold, you want to characterize that, but then you also want to characterize like two forms, so forms. So the thing you need is generalized geometry. So for those that don't know, so instead of having, well, I call it conventional geometry because I didn't know how to call it. Instead of having vectors, you're going to put vectors and one forms at the same footing. So instead of the tangent space, you have the tangent space and the cotangent space, which is called the generalized tangent space. And so instead of having the Lie bracket that you will have between the vector fields, now you have something which is a bit more sophisticated, which is this Courant bracket. And this Courant bracket is this form. I mean, at least you recognize one piece, which is just the Lie bracket, and then you have some terms that make it a nice bracket. It's a nice bracket, but it's not a Lie bracket because it's not antisymmetric. Okay. So that means that here, when the underlying manifold is a Lie group, you will have a Lie algebra. Here, what you have is another object, which is the object that's characterized by this Courant bracket and other things that Friedrich mentioned last time, which is a Courant algebroid. And that's the setting in which we will be working. Okay, so now that D-branes are modeled by direct structure has already appeared multiple times in the literature. It was also more explicitly described by Asarakawa, Murakami, Sasa, and Watamura, but also by Zabzin and Kerber. I will see in a moment what direct structures is. But the topological defect, also modeled by direct structure, was actually implicit in Kapustin and Setter. They never used the word direct structure, but when you read that, it is actually what they are using. Good. So now, what are these direct structures I've been speaking about? Well, okay, so this will be a math slide. So what is the mathematical motivation to have a direct structure? Well, somehow the mathematicians were in a fancy to have Poisson structures, symplectic structures, and foliation in the same object in one go. And this is direct structure. So what is it? Well, this direct structure is a subbundle of this generalized tangent bundle we just had. It needs to be Lagrangian, and then interestingly, it needs to be integrable. So it needs to close under this Courant bracket. And this is actually a very important property, because if you restrict it to the vector field, that means that this thing is going to close, and in particular is going to give you an integrable foliation, an integrable distribution. So that means that this object is going to foliate through manifold in different leaves. And let's call one leaf Y, and let's probably see that thing as the defect or the D-brane. And indeed, when you can show that in general, this direct structure is uniquely characterized by giving one of the leaves and the two form fields that lives on it. And then it has this form. So that makes it the natural object to describe exactly D-branes and defects. So just give me some examples, because I promise that Poisson structures and symplectic structures and foliations are living somewhere in this direct structure. So let's see that quickly. So Poisson structures, in general, are not invertible, so they are degenerate. So you cannot invert them as you want. What you need to do is actually to take a point and then to see at the neighboring points, well, can I invert that? And so on the points on which it will be invertible, it will be a submanifold. And actually, this condition is going to foliate the space, and that's exactly a foliation. And so on these submanifolds, I can safely invert my Poisson structure, and I have a two-form. And this is a two-form that describes this direct structure. And then the integrability condition is exactly asking that the Poisson structure satisfy that its Cartan bracket is 0, so that it satisfies this Jacobi identity. And symplectic structures are actually even simpler, because symplectic structure, well, it's a two-form, it's invertible, so there the foliation is trivial, it's just a whole manifold. And asking that it's integrable just means that it's closed. So by definition, it's what it is. And more generally, you have pre-symplectic foliation, where this thing might be degenerate. Good. Okay, but let's have some physics examples. So let me give one example that most of you know very well, which are D-branes in Wesel-Minowita models on some Lie group G. And so these things are characterized by special direct structures, which even have their own name, because they're very well studied in math, which are called Cartan direct structures. And they are defined by the data where, well, it turns out that you can write this definition. It's not very enlightening, but it boils down to having that Y are conjugacy classes, and that the two form, or it's pulled back by G, is this form, which is the one known for D-branes in Wesel-Minowita models. So you can describe them classically by Cartan direct structures. And now an even simpler example, the defect we now introduced, which was on the product space, was corresponding to a symplectic manifold. So it is one of these particular examples, and it's space filling. Good. Questions? Yes, Emmanuel? Yes. You need it because otherwise you don't have a foliation of the space. No, okay. So maybe I wasn't clear enough about that. So the name topological is a little confusing because it has nothing to do with the models what it has to do. The topological thing just means that you can do fusion with them. You can move them around. So that's what the adjective topological means. Does that answer your question? Maybe, okay. Then if it's not clear, you can ask me after the presentation. Good. Okay, and so now I can explain what this third way is of showing that the defect is topological that was proposed by Kapustin, well, shown by Kapustin and Setter. So there, well, they don't call it Dirac structure, but it's the same. So there you have a Dirac structure that's describing this foliation with a two form, but nothing guaranteeing this thing is topological. The thing that guarantees it's topological is that it's stable under what they call this generalized metric. So this fancy G was containing this G, is like the one that was containing the two metrics of the theory. And so asking that it's topological at the level of generalized geometry is just very simple. It just asks that in some sense this Dirac structure is stable under this map, this linear map. And this is actually, for those that knows complex geometry, it's very similar to having complex submanifolds. Good. Very good. And holding a second time. Oh, yeah, Alex? Yes, so you worried because the B field does not enter in that condition? Oh, the reason is because the B field is in the two form. So it's not here, it's there. Okay, good. Thanks for the question. That's good. I should have pointed that out. Okay. So now we can finally get to the way we propose to define fusion in a more fundamental way that was proposed before. So we still keep this Fourier-Mukai-Light operation. That seems to be a genuine thing to do. But the thing we want now to add is just to say that, well, since both things are direct structure, well, we should really formulate and try to work with these things directly. And so that means that instead of like having this picture where I move from one manifold to the other, what we propose to do is to have the Fourier-Mukai-Light transformation at the level of the Courant algebroids of these spaces, where now the object that we are going to move are the Dirac structures, going from one Dirac structure to one Courant algebroid to the other. And so that means that we have a Dirac structure here on this Courant algebroid. We're going to pull back to this Courant algebroid. We need to convolute it in some way, which I will explain in a second. And then we need to reduce it. But OK, nothing guarantees that this is well defined in any way. And luckily for us is actually that like Cevera and some mathematicians have already worked out in what kind of constraints you need to have on these Courant algebroids to be well defined. And this are actually exactly the Courant algebroids that Frédéric introduced. They need to be exact, which is very natural for nonlinear sigma model. In addition, they need to be G equivariant, so they need to admit some nice action of a Lie group on them, which we anyways have when we have, for example, Poisson-Lie duality. I won't enter into details. If you're curious, you can ask, but otherwise it's just a bunch of definitions. The point is that we know exactly when we can pull back and reduce Dirac structure in a well-defined way to have a Dirac structure at each stage. Now the problem is the convolution, really the thing that's going to encode T-duality. And so the thing that we thought, well, actually let's just do the simplest thing we can imagine, and you have a product operation actually on the space of Dirac structure that you can find in math literature. And that I denote with this circled star, and okay, it takes this form, and so it lives normally in the intersection of these two manifolds, and then you have this very simple form. And okay, with certain smoothness conditions, this is again a Dirac structure. Good. Now it seems that we have all the ingredients. So the result of doing that, so the fusion operation we postulate is actually exactly this, that you have this Dirac structure, you pull it back with just the inverse embedding map, you convolute it using this product, and then you reduce it to the fused manifold. And then the resulting object that you have at the end of the day of doing this is this for the submanifold and this thing for the two form. And as you might have noticed, this is exactly the fused word volume that Fuchs and Schweigert and Waldorf had, except that now it's well defined because we know that we always will have Dirac structures if we cook within this well-behaved class of object that we expect anyways. And we also have a formula for the two-form fields living on that gives a consistent Dirac structure. And okay, it does not come out of the blue this time. And you can actually check in the language of Cevera of Poisson-Lie duality in terms of Courant algebroids, where he actually has a section about how to do Poisson-Lie duality of Dirac structure that represent the D-branes using these reductions, and it's exactly the same as well. Okay, so yes, Dan? Yes. It's in F. Well, I mean, it's in this F. It's here. So actually, okay. So when you look at the Fourier-Mukai transformation, it's formal form, because it always takes actually a more complicated form, but it's always spiritually like this. Is the K? Well, okay, K plus the B fit. Okay. That's, let me then summarize and give some outlooks. So I argue that you can realize Poisson-Lee duality in terms of a topological defect, and that gave us like a free lunch to have an ansatz for the kernel of the Fourier-Mukai transformation, which coincides with one that's already known in the literature. And then I explained how you can use this fusion process to have the T-duality on D-branes, and then taking a step back from Poisson-Lee T-duality, I argue how one could define a fusion operation at the level of the target space, which is well defined and coincide also with the known cases. Good, so some open questions. Okay, so the first one, it needs a bit of background, so I need like 2 minutes for this one. So I already mentioned that Fuchs, Schweigert, and Waldorf have studied quite a lot topological defect in Wesson-Minow-Witte models. And as I mentioned, in D-branes, now I'm speaking about D-branes, in Wesson-Minow-Witte model have this very nice picture that the submanifolds they correspond to are conjugacy classes. And what they obtained for what the submanifolds of topological defect by some scattering computations on the world sheet was that the world volume of these topological defects are bi-dressing orbits, bi-conjugacy classes, sorry. So it's very nice. It's like you get a kind of mixed conjugacy class in the product space, and that realizes your topological defect. And so as Klimczek and Chevera showed, is that you can see the world volume as D-brane in Poisson-Lee duality as dressing orbits. So dressing orbits are like non-linear generalization of conjugacy classes. They are complicated conjugacy actions. But so the natural thing that you might expect then is that the topological defect in general for Poisson-Lee duality will be bi-dressing orbits. Well, we tried a little bit, we failed, but I still haven't given up on that idea. Okay, then another thing is that, so I told you that we studied integrable defects in Young-Baxter models. And integrable defects are actually very special cases of topological defect. So you might wonder, okay, can I also fuse these things? Well, it's also tempting, but it's actually very complicated because the problem with defects in all these different contexts is they all have their own definition, all they have their own construction, and it's very difficult to relate them. But maybe there can be a way to do that, and that would be interesting. Okay, okay, the last two are more contentious, and it's more like if you find that interesting or if you have any insight, please come talk to me. I would be interested to get more insight on these things, whether it's even possible. So I only spoke about fusion of a topological defect with a boundary condition. I never said anything about fusing two Poisson-Lee duality together. So why I did not do that is because we are still computing things about that, and it seems to be puzzling. Because why for normal T-dualities, you will always get that it's again a T-duality, and that it's again topological. For Poisson-Lee duality, it seems to be more complicated. And so that might point out that at least maybe at the level of fusion, Poisson-Lee duality is quite different from abelian T-duality. But that's okay, it's very preliminary. And then the last thing, which is probably even more contentious, but it's interesting to think about, is that, well, this fusion, it's not difficult to guess that you can see it as a kind of solution generating tool, right? You're in a system, you cross a defect, you get another system which is related by symmetry or duality. And okay, it was also studied as in this form by Bachhaus, Brunner, Sato, and Sagawara. And in particular, these people studied that in the context of generating non-geometric backgrounds and also T-fold. So one might hope that one can maybe have a step towards these things using fusion. But okay, this is okay. So thank you very much. Stop. Thank you. Advertisement. So I would like to draw your attention to a school, which is a Young Researcher School and Workshop. So if you don't know this is a school that normally is every year, and that focuses on a particular topic, mostly in integrability. And so this year topic is about an exact approach to the string worldsheets using CFT techniques and integrability. And this year it's going to be the last week of October in Stockholm. And so it's aimed towards a PhD student and starting postdocs, young postdocs. So if you're in this demographic, I strongly encourage you to go and check out the website. And if you're not in this demographic, go do that anyways, and please advertise. Okay, that was the end.
Thank you for the nice talk and advertisement. So do we have questions for Saskia?
Yeah, hi Saskia. Thank you for the very nice talk. It was very interesting to see this approach from the other side, so from the defect side. What I wanted to check with you, did you calculate the transformation rules for RR fields from your kernel of the Fourier mechanics?
That we did not do, but that's a very good point. Like
because I was wondering, I mean, so when we did this back then, you know, this was exactly our starting point, and we were saying we know the RR sector transformation rules from solution generating techniques, and then we were just taking them to calculate the kernel for the Fourier Mouquet transformation. And I mean, when you say they are different, then there are two possibilities, right? Either there is some subtlety. I mean, probably there are some possibilities and some choices for the kernels which result in the same RR transformations. Or, I mean, there are three possibilities. Or, I mean, you get different RR transformations than we already got from imposing solution generating techniques. Or we did something wrong. I mean, so some computational mistake.
Okay. No, that's a good point. Thank you for raising that. Actually, my guess will be the last one, because and the reason is as follows. So if you look at this operation, so this P and this P2, like in the way we computed it, it takes a Fourier Mouquet transformation where it's this funny integral that just kills all the one forms that are of lower rank. And because of that, you lose a lot of terms as well. So we did like a sort of back engineering, but doing this back engineering, we potentially lost a lot of terms that we didn't see at the end of the day. So in there, I think it's one of the reasons why it doesn't match. But then, indeed, it seems puzzling that these two things at the end of the day give the same result. It's in under some terms are redundant. I don't really know. And maybe the different Ramon fits. I didn't think about that option.
Yeah, because I mean, when you say it's really a different result, you know, so you should get perhaps different transformation rules for the Ramon fields. And then, of course, it would be interesting, because it's all connected to D-branes, right? I mean, we were more taking the effective field theory perspective, while you are really taking the nice classical D-brane approach. I mean, because from the classical worldsheet theory, you normally don't get the RR field transformations. So that's why it would be really interesting whether this gives different RR field transformations or whether there is some freedom in this kernel, you know? Yeah, and so that's why it looks like they don't match. Actually,
this Fourier Mouquet thing is very mysterious also just from a mathematical point of view, because mathematically, this Fourier Mouquet transformation is studied a lot by mathematicians, but in abelian context. And when you ask them about a non-abelian context, they say, and they just leave it in peace. So that makes it probably also complicated because there are no formal results on that once we want to move to Poisson-Little duality. Yeah, no, I agree. It's a very interesting question.
Other questions?
You said your fusion was a bit funny for the Poisson-Little duality. Could you elaborate on what exactly happens?
I can say that off camera because I don't want to be on video if it's wrong at the end of the day. Yeah, I would.
And then could you maybe just say again, what in the target space, what was the defect that encodes the Poisson-Little duality? Because it's not the D-brane. It's not a D-brane, right? So,
no, I mean, like the big difference between D-branes and defects is that they don't even live in the same space, because one is on the target space and one is on the product space. So it's why like the defect is living here and the D-brane is living there, and that's the thing you lift, and there it's then you can convolute it with the defect, and then the result you just push back.
Okay, thanks.
Yes. Okay. Thanks for your question.
Thanks for the talk. Can you elaborate on this screen condition that you have? You said it was a little bit technical, this GF square equal 1. Can you elaborate on that?
Can you say which?
This condition you have with the generalized metric and the flux, that the square of that is equal to 1, you said that perhaps you can elaborate on
Yeah,
the...
it's just because you have a DD signature. Your space on the space is not going to nicely divide into the tangent and the normal one. You have, and the thing that you miss because you have this mixed signature is called the screen distribution. And it just turns out that when you do the computation that Setter and Capistin did, is that the condition is on that screen distribution exactly. So it's just a technical detail actually.
Okay, thank you.
Hello. I have a question about the slide that you just flashed in, and about this model that you have, what is S1 plus S2.
Where do I have S?
Sorry, I mean when you interpret Poisson duality as a in terms of defect.
So the very last one.
There was like an action that you wrote that it's like two terms, and then you had the pullback of the connection. Yeah, sorry, I don't remember where that was.
Maybe you can show afterwards.
Yeah,
on the
okay,
slides.
yeah, sorry. Yeah.
Okay, no problem.
Any more questions? I don't see any other hands, so if not, let's thank Saskia again.